Hi everybody, this is Dr. Bricker here with a video for Chapter 22, Part Number 2, Connecting Voltage and Current. So a battery is a source of potential difference. We talked about this last time, or voltage in other words. It's an entity that can do something for us. It's a device that can do something for us, I should say. So the current that flows through a wire that connects battery terminals is because of this potential difference. So if you have a battery, you establish a potential difference. Once you connect a wire there, the wire experiences the voltage of the battery, and you can actually get electrons to move around then. Because the ends of the wire are connected to the battery, the potential difference between the battery posts is the same thing as the potential difference that's across the wire. And as you can see here, and that allows electrons to feel a force, and they feel a force, they move through the wire. That's really what current is. So two factors determine the current: how much voltage you actually have, or potential difference in this case, and some properties of the wire. You know, what's the wire made out of, that sort of thing. How wide the wire is, how long the wire is. So if you increase the potential, that's what you're seeing here. You double the potential, you double the current. It's like making the ski lift twice as big. You can get more out of that. On the other hand, if you take the wire and you make it a lot thinner, the path for the electrons to move is not as easy. Or if you make the wire really long, it makes it harder for the electrons to move through it. So pretend you're walking through a hallway with nobody else around. You can walk through the hallway really easily. Now if you start to put people in the hallway and you try to make your way through the hallway, you're bumping into people, slowing down. That's in my analogy, that's making the hallway thinner, or making the wire thinner. Or if you make the hallway really long compared to short, it would be harder to get through there as well. Okay. Copper versus iron, there's a difference in how many charge carriers are available, so we have different resistance. Something called the resistivity of the wire. So copper wire carries larger currents than iron, because copper has more free charge carriers than iron. Okay, so there's something called resistance. It's a measurement of how hard it is to push charge through a wire. So the charge is proportional to the voltage across the wire, inversely proportional. What I'm trying to say here is the current is proportional to the potential across the wire, inversely proportional to the resistance. So the smaller the resistance, the more current you have. Okay, so that's really what resistance is. If we do a little bit of algebra to the last formula, potential difference divided by current. So this would be voltage divided by amperage. We have a new unit here, an ohm. So it's a measurement of resistance. The more resistance you have, the less current you have for a given potential difference. Okay, good. We're working towards something called Ohm's law that we'll see in this chapter, actually. Well, so let's take a look at this one. The current through a wire is measured as the potential difference is varied. We'll do a lab kind of like this, actually. So you can see here, let's see what's actually being graphed. Voltage on the horizontal axis, current on the vertical axis. Okay, so as you can see, as the voltage increases, the current increases. And we want to know what is the resistance of the wire. Okay, so if I go back to the last screen here, this would be voltage divided by current. Okay, so the resistance is the inverse of the slope then, because we've graphed I on the vertical axis, V on the horizontal axis. It might have made more sense to put delta V here, I over here, and then the resistance would be the slope in that case. Okay, so if you figure out the slope, the inverse of the slope turns out to be 0.02. Right? Slope, rise over run. So pick a couple of convenient points. The rise would be 50. If I go from 0 to 50 amps, divided by the run here would be 1 volt. So 50 over 1 is the slope. The inverse of that turns out to be 0.02. This is similar to 22.3 on the third homework set. Okay, very good. The glowing element in an incandescent light bulb is the filament, a thin piece of tungsten wire that's heated by electric current through it. When connected to 120 volts of an electric outlet, we're pretending that the voltage in your house is just something called DC. That's this number. It's not really the case in real life, but that's okay. So pretend we've got 120 volts. We've got a 60 watt light bulb. That's just describing the light bulb. And we have a current of 0.5 amps. We want to know what's the resistance. Okay, so we know the voltage and we know the current. We can come up with the resistance. So the resistance then is the voltage divided by the current. So 120 over 0.5, 240 volts. As you'll see below, the resistance varies with temperature. So this value holds when only when the bulb is glowing and the filament is hot. Okay, so there is a temperature dependence. Temperature really just means how fast molecules are moving. So when the temperature of the wire goes up, particles in the wire are moving faster, and it's harder for the electrons to get through there. That's the way of thinking about it. Okay, so resistivity. This could be confusing. It's called resistivity. It's a property of the wire. So copper has its own resistivity. Iron has its own resistivity. Now it's related to resistance. That's what makes it tricky maybe. But the resistance depends on how long the wire is, how thick the wire is, what it's made out of. In other words, resistivity. The resistivity is just a number associated with whatever it's made out of. Okay, materials that are good conductors have low resistivity. Poor conductors have high resistivity. Okay, and that there is a temperature dependence on resistivity too. So copper's good here, 1.7 to the -8th. Cell membrane on the other side of the table here, like 36 million or something like that. Ohms per meter. Blood, seawater, all mixed in here, aluminum, tungsten, iron. You can see copper is about 10 times better almost than iron. You can make wire out of iron, but it doesn't conduct electricity as well. Okay, so just some values here. Muscle versus fat. Remember the first picture that we saw from this chapter, the body fat device works on this principle that muscle has a smaller resistance to the flow of current than fat does. Okay, and here's the formula. Resistance then, you already have one for resistance, how it depends on voltage and current. Here's a way of calculating the resistance just on how long a wire is, the cross-sectional area of the wire, and the resistivity. So the resistivity doesn't change. It does change with temperature, but resistivity is just a property of whatever the wire is made out of. The resistance depends on how long it is and the cross-sectional area. Here's some typical numbers here. So if you're rich, maybe you want to make your house wiring out of silver. I mean, you save a little bit on resistance if you do that. Okay, all the way up to glass and rubber. These are insulators up here. So let's take a look at that formula in a little more detail. So by cross-sectional area, we mean this. So a wire is typically this shape. Whoops. Like a cylinder. Here's the length of it. That's the length in the formula. And then this would be the cross-sectional area. So the area of a circle, if you remember, is pi r squared. Okay. You don't have to make a wire out of a cylindrical looking shape, but typically that's what they look like. You could make it out of a square one if you wanted to. Okay. So it turns out that wires don't have a lot of resistance, but they do have a small amount of resistance. Here's an example. The filament of a 100-watt bulb carries 0.83 amps at an operating voltage of 120 volts. What is the resistance of the filament? And if the filament is made of tungsten, a diameter 0.035 millimeters, how long is the filament? Okay, so we can get the resistance from what we've done before. Delta V is equal to I times R. So then R is delta V over I. Okay, the voltage here is 120 volts divided by 0.83 amps. Okay, let's see what that comes out to be. Okay, so 120 divided by 0.83, about 145 or so ohms. That's what resistance is measured in. Now, if you have the resistance, here's another way of looking at resistance, depending on what it's made out of. So we've got rho L over A. Okay, and we're trying to figure out how long it is. So here's the resistance value. Now it's tungsten, so we can go back to the formula for tungsten to get the resistivity of tungsten. Resistivity equals, let me go back. Okay, let's see, they said when it's a normal operating voltage of 120. So let's assume that it's actually operating. So 5 times 10 to the minus 7th. 5 times 10 to the minus 7th ohms times meters. Okay, now they give us the diameter, 0.035 millimeters. From the diameter, we can get the area. So let me regroup here. We're trying to figure out the length. So the resistance, multiply both sides by A, divide both sides by the resistivity, will give us the length. Okay, so the resistivity I know because it's tungsten and it's operating. Check mark. The resistance we got from the first part, check mark. Now the area is going to be the area of a circle. Okay, so I'm not going to put the numbers in, but you saw from the last slide, this was pi r squared, or you can write it like this, pi diameter squared divided by 4. If you put diameter divided by 2 into the formula here for the resistance, you square that term, and that's why you get this number. Just be careful, the diameter has to be 0.035 to the minus third in meters. Okay, and then you have everything. Then it's just a matter of putting the numbers together. Okay, very good. So this will come out in meters then. Okay, let's look at the next slide. Wire 2 is twice the length and twice the diameter of wire 1. What is the ratio of R2 to R1? Okay, so wire 2 is twice as long. Let me write this formula. Okay, we've seen that before. Or I could write it as then pi r squared for the area, right? Resistivity times the length divided by area, but the area is pi r squared. That's what makes it a little bit tricky, because the resistance is squared in the formula. Okay, so wire 2 is twice as long, so it would have twice the resistance for that reason. But the diameter is twice as big, so that would make it 1/4 as much resistance. So the fact that it's twice as long increases the resistance by a factor of 2. The fact that its diameter is twice as big, don't forget, that makes its radius twice as big. So in the formula you have to square it. So the contribution from the length is 2 times more. The contribution from the diameter being twice as big is, you got to square it in the formula, 1/4 as much. So it turns out to be 1/2 as much when you put those two factors together. Okay, good. So length makes it twice as much. The diameter being twice as big makes it 1/4 as much. Both of those factors taken into account, we've got 1/2 as much. Okay, so the length of a light bulb filament. We calculated in example 22.4 that a 60-watt light bulb has a resistance of 240 approximately at the operating temperature. The resistivity, good, we saw this too. If the wire used to make the filament has this diameter, a typical value, how long must the filament be? So don't be surprised if it's really long, actually. So let's take a look at that. So we know the resistance, the resistivity, the diameter. We want to figure out how long it must be. Okay, and we're assuming again that it's got that cylindrical shape like this. Okay, and that's the cross-sectional area. Okay, so pi r squared. So pi times 2 to the minus 5 meters squared. Right, it was a really small, thin wire. So 1.26 to the minus 9th square meters, that's the cross-sectional area. Okay, so if you solve for L in the formula, right, this started as this. Do a little bit of algebra, solve for the length, you get this formula. Put everything together, 0.6 meters, so over a half meter long. That's a lot. It's just all coiled up. Okay, so 0.6 meters. Quite long, nearly 2 feet. This result may seem surprising, but some reflection shows that it makes sense. The resistivity is low, so the filament must be quite long. Okay, so that's an old school light bulb. Okay, so different tissues in the body have different resistivities. Fat has a higher resistivity than muscle. Kind of mentioned that already. So higher resistance indicates higher proportion of fat. So when you're getting one of these body mass calculations, like in the picture in the beginning of the book, that's what's being used here. Okay. So an image of a patient's torso generated from the resistance between pairs of electrodes shows decreasing resistance in red and increasing resistance in blue. So you can tell what the tissues are made of. So blood is a better conductor than tissues of the heart and lungs, so the motion of blood decreases the resistance of the heart and increases of the lungs. And you get this kind of picture made from electrical properties, what we actually are made out of, different things, blood versus muscle and fat. So in a patient with circulatory problems, any deviation from normal blood flow would lead to different pictures. So if you know what the picture should like, you compare it to the picture that you get. I will make a separate video for the homework 3 help, by the way. Okay, so pretty cool. You don't have to cut somebody open and look at what's going on. You can make this sort of a picture. So Ohm's law and resistor circuits. So Ohm's law describes the relationship between voltage and current. So not everything obeys Ohm's law. If it's a conductor, it'll obey Ohm's law, but there's semiconductors and things like that. So as long as the current is proportional to the voltage and inversely proportional to the resistance, like this, then it follows Ohm's law. So usually this is kind of like V over here, I over here, and then the slope would be the resistance. Okay? So materials that follow Ohm's law are called ohmic. Not everything is like that, but most things we'll deal with in this class are. Okay? So this graph is the opposite. I prefer this one that I just made versus this graph. The slope is 1 over, the resistance is 1 over the slope there. Okay? Very good. So resistors are circuit elements that are designed to have certain resistances for practical purposes. Here's a symbol for a resistor, measured in ohms. So this could be like 10 ohms or something like that. I'm just picking out a value. So they're used for a lot of different things. We talked about electric blankets. That's really what's going on there. Resistance to the flow of electrons. The metal actually heats up. Different things like that. Oh, here's a heating element in a toaster. If you use a toaster today, as charge moves through the resistive wire, the electric energy is transferred to thermal energy, heating up the wire. Okay, it's really cold out today and this whole week, so maybe you're going to be using your rear window defroster of your car. Okay, so lots of different things. I mean, I'm talking about using resistors to heat things up. They're used in communication circuits for setting different impedances, lots of different things. you probably have seen them before. Maybe you didn't know they were actually resistors, but they're color-coded like this. So the different color coding means different resistor values. So if you're into electronics, you could look at this resistor and say, okay, it's black, red, that means a certain thing. Maybe that's 10 ohms or something like that. I can't remember what the scale actually is. Okay, so they indicate resistor values and also the tolerance of the resistors. Okay, neat. So a resistor whose resistance changes in response to changing circumstances can be used as a sensor. So the resistance of this night light sensor changes when daylight actually strikes it. So the sensor has a certain resistance. When light hits it, the resistance changes, and then maybe that triggers something to happen with this night light. Okay, maybe you have one of these outside or something. Okay. So when you press the lever on a toaster, a switch connects the heating wires to 120 volts. The wires are initially cool, but the current in the wire raises the temperature until they are hot enough to glow. And as the wire heats up, how does the current in the toaster change? So as the wire heats up, the resistance of the wire goes up. So if the resistance goes up of the wire, but the voltage stays the same, the current has to go down. So that's probably what it's going to say here. As the wire heats up, the resistivity increases, so the resistance increases. Because voltage stays the same, and increasing resistance causes the current to decrease. Okay? So here's the formula, delta V, I times R. So if R gets bigger, I must have to get smaller. Okay, good. So the wire's temperature increases, the current decreases. If it worked the other way around, you kind of have a runaway effect, and you'd burn your food, right, if it started off the other way around. Okay. So in a light bulb, connections to the filament in the bulb are made at the tip. So there's here's the inside part. You can think of this as the resistance part. Now let's take a look and see how this is actually connected. If you've changed the light bulb in your car, you might have already experienced this. So one of the wires is connected down here, and then there's an insulator. That's what the gold part is here. You can see the insulator. But one of the wires of the filament is connected here. One is actually connected to the side part of the wire. So when you connect this to a battery, that's the connection you're making. One part of the battery connects here. One part connects here. Maybe through wires, though. Or maybe through the socket that you actually put it into. And you make the connection that way. As you can see here, this is maybe a better picture. Wire connects to the base part, another wire connects to the side part, and then you can get current to flow through this bulb. So in a circuit using a battery, the light bulb and the wires, the light bulb has a resistance of 3 ohms. Wires, on the other hand, have a much smaller resistance. For all practical purposes, an ideal wire then has no resistance. Wires do have some resistance, but it's really, really small. Okay. So here's how this might look in a voltage, how the voltage is actually used. So if you have a 10-volt battery, you're applying that 10 volts over the entire circuit that it's connected to. So current flows through all 3 elements, the wire, the resistance, and the other part of the wire. So the circuit might look something like this. This is the symbol for the battery. So we go through one wire, we go through a resistor, and then we go back to the other side. This is the positive side, negative side. And then we're pretending it's conventional flow, so current's going to flow like this. So the wire doesn't have any resistance. It really does, but really, really small. So we don't have to use up any of the voltage there. None's being used up, right? The voltage is staying the same here. The voltage is sort of being used here to propel an electron, or our pretend positive charges, through the resistor, and then we don't have to use anything of the battery here because it's a wire. It doesn't have any resistance. Okay, that's if there's no voltage having to be utilized in the wire. So current moves in the direction of decreasing potential because we're using these pretend positive charges. Okay, so this is kind of the connection between what we've done before with electric fields and voltage and what we're doing now. So the electric field in a resistor carrying a current is uniform, so it's a constant electric field. The strength, we saw this before in the previous chapter. The electric field is delta V over L. Did homework questions on it, that sort of thing. Okay, let's take a look at this quick test. In trial 1, a battery is connected to a single light bulb and the brightness is noted. Here's a battery connected to a single light bulb. Now in trial 2, a second identical light bulb is added. How does the brightness of these two bulbs compare? This trial versus this trial. How does the brightness of each of these two bulbs compare to the brightness of the single bulb? Okay, so the brightness here is going to be half as bright as here. The reason is we've got two light bulbs, so it's like having two resistors connected. The battery has to power two bulbs. Here it's only powering one bulb, so the overall resistance in this circuit is twice as big as the overall resistance in this circuit. So trial 1 is going to be brighter. So trial 2 is not as bright. Okay? All right, very good. So a thermistor is a device whose resistance varies with temperature in a very well-defined way. So a certain thermistor has a resistance of 2.8 kiloohms at 20 degrees and 0.39 at 70 degrees. Okay, good. This is used in a water bath in a lab to monitor the temperature. So it's connected in a circuit whose voltage is 1.5 volts. It's a battery, and the current is measured. What is the change in current in the circuit as the temperature rises from 20 to 70? Okay, so this is a specialized device. The temperature is going up, but the resistance is going down. So it's a specially made device. It's kind of opposite of what we've been talking about with the temperature and resistance having different, different values. So this is a specially made, unique device. Okay, we can figure out the current at this temperature. So delta V over R, using the formula that we had before, 0.54 milliamps. At 70 degrees, we've got more current, 3.8 milliamps, same formula. So the difference in current then would be 3.3 milliamps. And that's how you could kind of take this temperature change that you're getting in the bath and converting it to a current, and then maybe that you see that on a meter or something like that, so you can figure out this is what you could measure, and then it's proportional to the temperature change, and you can construct a meter that way. Okay, very good. So modest temperature change leads to a large change in current, which is reasonable, intended to provide a sensitive indication of temperature change. Okay. Small change in temperature, large change in current. And then again, you can create some kind of device to measure this. Energy and power. So a battery not only supplies a voltage, but it also supplies energy. So we're taking chemical energy in the battery here and transferring it to really kinetic energy. So chemical energy first goes to potential energy of the charges, and then we use that energy to drive electrons through the circuit, through the light bulb, heating a light bulb up. Okay, and as you know from batteries, they don't last forever. Eventually you use up all the energy. So a charge gains energy. This goes back to the last chapter actually, as it moves through a potential difference. So that's kind of like the ski lift analogy. The voltage of the battery, we're calling this squiggly E now. So the amount of energy that the battery actually supplies us then, from what we've done before, remember this is potential energy, Q times delta V It's just that the delta V of a battery is called the squiggly E. So this is how much energy we have. Okay, so that's to lift up a positive charge from the negative side of the battery to the positive side of the battery, just like the ski lift analogy. That's how much energy that we have stored. We're at the top of the ski lift. We can do something now. Okay, so the power then is, going back to physics 220, the rate of energy transfer. So delta U over delta T, that's power, remember, joules per second. But the energy part is Q times E, right? We saw this from the last slide. And then delta Q over delta T turns out to be the current. So finally, the power of the battery is the current times the voltage. So that's the power delivered by, it says source of EMF. In this case, we're talking about a battery. So joules per second or watts. Okay, good. Here's an example. Car battery, 12 volts. When the car's starter motor is running, the battery current is 320 amps. That's a whole bunch of amps. What power does the battery supply? So from the formula, it's I times squiggly E. So 320 times 12, 3.8 kilowatts. It's a lot of power. 320 amps is a whole bunch of current too. A lot of power, about 5 horsepower, but really it's turning over your engine, so you have to have something that can supply that amount of power. So really, car batteries, they stay in your car, they're outside, maybe they're in your car in the garage or something like that, but they go through a lot. They're going to really be tested this week, right, with the temperatures dropping too. Okay, so old reliable car battery. I mean, they sit there for years and years, right? Okay, so we're taking chemical energy, turning it into electrical potential energy, which then powers charges through our circuit. So electrical potential becomes kinetic, and then the kinetic energy of the charge carriers becomes thermal energy as we go through a resistor. So lots of energy transformations going on. Okay, so here's the battery. Here's a way of thinking about it. It takes a positive charge, doesn't want to go here. This is the ski lift up to the top, and then it could fall through the circuit, make its way through a resistor and back around. Okay, so the potential, the voltage set up by the battery provides an electric field through the entire circuit. Okay, and then you get back to this side, and then the escalator lifts you back up through chemical processes. Okay, so the net result of a circuit consisting of a battery and a resistor is the battery delivers the power, and it's going to be used up it's going to be utilized in the circuit. So the power that the battery provides is used in the resistor. So that's what we have here. The power that the resistor gets, it's going to be the same thing that the power delivers, or that the battery delivers. Change in energy divided by time, same thing that we did before, delta Q over delta T then, because this is Q times the voltage on the resistor. So same thing. Turns out to be I times V. So whatever the battery supplies is utilized by the resistor. Okay, kind of like power out is equal to power in. That's what we see here. All right, very good. The rate at which the battery supplies energy is exactly equal to the rate that the resistor dissipates energy. It's got to go somewhere. Okay, so here a resistor is connected to a 3-volt battery. The power is 1 watt, 1 joule per second. The battery is traded for a 6-volt battery. The power dissipated is now. Okay, so we have this, power I times V. So the V that the resistor gets is the same thing that the battery is providing. There's a lot of ways of writing this if we look at what we had before. V is I times R. So I can take this for V, plug it into what I have here, and I would have I squared times R. So I've taken V, plugged it in here, and I have I squared times R. Or I could solve for I in this formula. V over R is I put it back into the original formula for I, and then I would have V squared over R. So 3 different ways of looking at power. I times V, I squared times R, or V squared over R. So hopefully from this, we could figure out what's going on here. Okay. So what we're not changing is the resistance. The resistance is staying the same. We're increasing the voltage of the battery. So the voltage goes from 3 to 6. Same resistor though. So we've got to figure out a relationship between V, R, and power. That's what the last one actually has here. V squared over R. So the power was initially 1 watt when the voltage was 3. How much is the power when the voltage is 6? So it's twice as big. So if the voltage is twice as big, right, going from 3 to 6, the power is going to have to be 4 times as big, right, because it's proportional to V squared. Okay, so if we used 1 watt at 3 volts, doubling the voltage of the battery is going to make the power 4 times as big, or 4 watts in this case. Okay, good. If you want a more rigorous way of working it out, we can set up a proportion. So power 1 watt over power, we don't know, watts. Maybe I'll do it like this instead. P1 over P2 is equal to V1 squared over V2 squared. So by setting up a proportion, that's what I mean. And then we can, plug in the things that we know. Running out of room here, but let me try to do this over here. Power 1 was 1 watt. Power, in the second case, we don't know. Voltage 1 was 3 volts. Don't forget the squared in the formula. And now we went up to 6 volts. So then you can figure out power 2. Do that over here. Power 2 then turns out to be 1 watt times 6 volt squared divided by 3 volts squared. So 36 divided by 9 is 4, then 4 times 1. This would give you 4 watts. Either way of looking at it is completely fine. You can do it the way that we talked about initially, just knowing that it's proportional to V squared, so doubling it would make the power 4 times as big. Or if you want a little bit more rigorous, we could take a look at this way of doing it, right? Just setting up this proportion. There is a third way of doing it, actually. If you wanted to figure out the resistance from the first information and then just use that resistance here to actually calculate the power, you could. So how would you do that? 1 watt, this is 1 watt, that this is 3 volts, you could actually figure out the resistance. And then knowing the resistance, then you could figure out the power for the second case. Then this would be whatever the second voltage is. Now you know the resistance and get the power that way. So several different ways of solving this problem. Okay, so 4 watts. So let's take a look at another example here. How much current is drawn by a 75 watt bulb? Okay, so that's, that this is power, right, because of the units. 120 volts. We can model the light bulb as a resistor. Okay, so we know the voltage, we know the power, and we're trying to figure out the current. Okay, so this is kind of a more straightforward way of applying this. This is power, current times voltage. Just put the numbers, solve for a current. That's what's being done here, and then we can get the current that way because the voltage is given. Okay, so 0.63 amps, quite a bit different than a car starter. Okay, and this is several different ways of writing the power formula. We've seen this a couple of slides ago. Okay, and again, we'll take a look at this when I make a homework help video. Okay, so that's really all of Chapter 22. Make sure you go back through and do the homework. I'll make you a homework help video. Any questions, just send me an email, and I will talk to you soon. Bye-bye.